Good evening, everybody. Bob DeVance with the McKinney Amateur Radio Club, K5CRX. We'll be going into session 2 tonight of our amateur extra license prep class that we've been doing. As I said, this is the second session, 2 of 10 that we're targeting to do. Our subjects for tonight, we will finish up what we started last time, which was called Skywaves and Contesting, a little bit misleading perhaps, dealing largely with propagation and waves, the ionosphere, those kind of things. Then we'll talk a little bit about what is called outer space communications, namely looking at satellites and Earth-Moon bound, some of those kinds of things. And then winding up with visuals and video mode, that is to look at slow scan TV, fast scan TV for amateur radio, and some of those things in the visual world that we do as hams. So with that, just in a couple of minutes, we'll get started. Welcome everybody to tonight's session. Okay, anything that you say now may be used against you. I guess I don't know. No, not really. We'll just have a good time like we always do. All right, welcome everybody. Glad to have you. This is session 2, McKinney Amateur Radio Club's special class for the Amateur Extra license. We're covering the highlights of the technical sides of that particular thing, not covering the rules and regulations, but just about everything else. And so don't want to spend a lot of time on pleasantries. Want to just go ahead and share my screen and let's get started. So here we go. I'm going to share that one, share it, and then start the slideshow on down a ways. Oh, right there. Slideshow for current slide. Okay, everybody see me okay there? Screen's okay?
Yes.
E3B04 down to the slide.
Yep.
All righty, then here we go. We actually covered this last time. We'll just run it by briefly by way of review. Extraordinary and ordinary waves have to do with, I got to move something just a second. There we go. Have to do with propagating elliptically polarized waves created in the ionosphere. It's one of those little things we've got. And we're not going to talk about if there's an answer that you want to discuss, stop me and we'll take the description right after the question. We have time. We can discuss it if you need to. Circularly polarized electromagnetic waves. What are they? Rotating electric and magnetic fields. By the way, how do we get a circularly polarized wave anyway? Anybody know?
It's out of phase by 90 degrees.
Basically, that's it. We can actually use different kinds of antennas, depending on the frequency a lot. We can actually generate the wave with an antenna that will circularly polarize the wave. You do have some loss over what you would have with a horizontal antenna or vertical antenna for that, but for satellite stuff, that seems to work very, very well. Okay, Voice of America CAP program has to do with HF only. Very nice little program. We looked at that last time. Short-term radio blackouts come as a result of solar flares. Don't last long. Hence the name short-term, usually an hour or so. And which amateur band is long path propagation most frequent? It's actually 40 and 20. And you remember, long path is where we go backward around the world. Instead of going the shortest distance, we go the longest distance, go all the way around the world backward to wherever we're going to make a connection. And 40 and 20 are the two bands most frequently used for that. Okay, which of the following paths is most likely to support long distance propagation on 160 when it gets dark? Which is generally the case anyway with those lower frequencies. Maximum range of ground wave propagation change when the signal frequency is increased. It goes down. They're inversely active, so it goes down, decreases. What should be done to continue a long distance contact when the maximum usable frequency for that path decreases due to darkness? If the maximum decreases, then we just go down a little bit to a lower frequency, is essentially the idea. Effect of chordal hop propagation. You'll remember chordal hop is where the signal goes up, hits the ionosphere, and rather than bouncing back down to the Earth, it bounces off of itself in the ionosphere before it finally does come back down to the Earth. And with that, we get a little bit stronger signal because of that, since it doesn't have to bounce down to the Earth. So you can guess probably what the answer is. That does the multi-hop normal uses the Earth as a reflector. This one does not. So it's a little stronger signal. What is it? We just talked about that. Successive ionospheric refractions without intermediate reflection from the ground. It just stays up in the ionosphere until it gets ready to come down finally and permanently. Transequatorial propagation is that dealing with things that are around the Earth's equator. Generally, there's a distance above and below the equator that if sites are those within that distance, they're able to communicate at special times during the day. That distance is generally 2,000 to 3,000 miles. Overpath perpendicular to it, meaning that the person would be straight down from the equator, and somebody else would be straight up from the equator, using north and south as up and down as a reference. The 2,000, 3,000 miles is the answer they're looking for. Approximate maximum range for signals, however, is a lot more, which is 2,500 miles either side of the equator. So it really is not that big a difference from the previous question. So about 5,000 miles max. What time of day? It'd be afternoon and early evening, because we allow for warming of the ionosphere to happen during the morning and noontime. And then after that, once things are warmed up, then the transequatorial propagation seems to work better, afternoon and early evening. Which of the following is indicated by sudden rise in radio background noise across a large portion of the HF spectrum? What is going on out there? Coronal mass ejection throws down some stuff, or a solar flare throws down some stuff toward the Earth in the form of X-rays and UV rays, and wreaks havoc with the ionosphere, causing a lot of noise. The A index and the K index. As those increase and go up, that means the disturbances in the Earth's geomagnetic field has increased as well. And there are websites, places you can go, including the ARRL's website, where you can get that information if you want to track it. Which of the following signal paths is most likely to experience high level of absorption when the A and the K are elevated? Any guesses? Has to do with the aurora, the auroral oval. With the auroral oval is an oval-shaped or elliptical-shaped area generally over one of the magnetic poles, where the aurora would most likely occur. The value of B sub Z, and this is dealing with interplanetary magnetic fields at this point. As we know, more north and south poles of magnets that tend to attract each other. The Earth has north and south pole, as does the sun. And when those two come into an alignment so that the north and south poles, the south pole of the sun, north pole of the sun are lined up, then we get into some interesting things. The value of that represents north-south strength of the interplanetary magnetic field, north to south. We're not going to spend a lot of time on that. I don't know that I've ever had a reason to know that before, but it's there, and it is a question on the test. Okay, what orientation increases the likelihood that these things will happen? It's going to be southward. Which of the following indicates the greatest solar flare intensity? You remember we looked at a little chart last time, and the class X was the greatest greatest intensity. Class X solar flare. What type of data is reported by amateur radio propagation reporting networks? Digital and CW. We don't do that in voice. We just send normally a fairly light signal out, and we check it on the internet to see how we're being received. Which of the following is the space weather term for an extreme geomagnetic storm? And we're back to that chart one more time. That's a G5 storm. G1 through G5 is the storm levels, and a severe one would be a G5. 304A solar parameter refers to measuring the length of light. The UV emissions are measured in angstroms. UV emissions at 304 angstroms correlated to the solar flux index is what 304A measures. So you see the 304 connected, and someone else just came in. Okay, we'll do that. That's Jerry. Okay, good deal. Okay, what time of day does sporadic E propagation is it most likely to occur? We mentioned sporadic E, but sporadic because it comes and it goes and it happens when it feels like it. What time of day is it most likely to occur? During the daytime, between sunrise and sunset, all day long. And that's because as the sun is heating the ionosphere, various things are coming from the sun toward the ionosphere, those conditions change that will reflect things back and forth. So generally that's why it's done during the daylight hours. What time of year is it most likely to occur? In the summertime, when everything's the warmest, obviously. When a meteor strikes the Earth's atmosphere, a linear ionized region is formed at what region of the ionosphere? That is the tail of the meteor. Where is that located? It's located in the E region. You remember the E region is one of those which disappears at night. So this would be a daytime thing. Which of the following frequency ranges is most suited for meteor scatter? It's the upper frequencies, namely 28 to 148. And which of the following digital modes is designed for meteor scatter communications? And that was one of those crazy ones. You just kind of have to remember it. MSK. I've forgotten what the M stands for now. Can somebody help me out? What does the M stand for in MSK? Anybody remember? No? Okay. I don't remember either right now. But anyway, MSK 144, I think that's the only place we really deal with MSK 144. Let's see. Did I have that defined back there? No, I don't have anything there that tells us what MSK stood for. Okay. What information replaces the signal to noise ratio when using FT8 and FT4 in a VHF contest? We normally send them our grid square. That's just kind of by convention what we do. What is the most likely result in auroral propagation? Now, auroral propagation is when we have the aurora showing up in the north or south poles. And if we're under it, our signals get absorbed by it. However, if we're not there, we can actually bounce signals off of it. However, when we bounce them off of it, they don't bounce very well. You get more like noise burst really than they are standard CW signals like we would really expect to see. So the result in the propagation there is severe geomagnetic storms. The two go hand in hand. Which of these emission modes is best for that? And it's absolutely CW. And again, as we said last time, the CW, instead of coming through as a sharp on-off, like it would normally be for a CW make and break, this is more like the old spark type transmitters where you have noise bursts representing dots and other noise bursts that sound like dashes. You kind of have to be very flexible and interpret those things. How does the VHF, UHF radio horizon compare to the geographic horizon? The radio horizon will tend to bend just a little bit around the geographic horizon, violating the rule we usually say that VHF, UHF is always line of sight. It'll give us about 15% more distance as it bends just a little bit around the horizon. So 15% farther is the answer. How are the component fields of the electromagnetic wave oriented? And we always want to remember anything we can about right angles and 90 degrees. These are right angles in this particular case. The out of phase is what rules that one out. Just right angles works in this, the two waves, two component fields. Atmospheric ducts are capable of propagating microwave signals, often from over what kind of a geographic figure? You remember the atmospheric ducts is kind of like some duct work we would have for air conditioning. We would compare it to in a house, but it's up in the ionosphere, and it would allow a signal, say from a repeater, a VHF repeater, to go through maybe 200 or 300 miles and then come back down someplace else. For a short period of time, it appears, and then it just disappears. But it generally works over large bodies of water or something similar to that. What determines the speed of magnetic waves through a medium being something like coax, for example? The index of refraction, which is the inverse of velocity factor. Okay. Typical range for tropospheric ducting, or troposcatter is the old term we used to use. Tropospheric ducting propagation of microwave signals, generally 100 to 300 miles. In most cases, it doesn't go a great distance. And that's generally about right. In what direction does an electromagnetic wave travels? Look for right angle. Right angle to the electric and magnetic fields. What type of polarization is supported by ground wave propagation? This is waves that travel primarily along the ground as opposed to going into the atmosphere. And we use a vertical antenna for that, and it goes right along the ground and supported by ground waves. We'll actually let it jump over some geographic features such as hills and such that can actually let it do that. How should you generally identify your station when attempting to contact a DX station during a contest? Send your call sign a couple of times. Don't get carried away. Don't hog it. One of the little tricks that I found, sometimes you throw your call sign out there, and if you're mobile, say mobile, sometimes that will get their attention. If you are running QRP, by all means, throw your call sign and say QRP. That will oftentimes make it happen. Why do DX stations transmit and receive on different frequencies? Recall for DX, oftentimes they will transmit on one frequency, they'll receive on a different one, and they will advertise it as, like for a DXpedition in particular, they'll say, we're transmitting on this frequency, listening 10 up, meaning 10 kilohertz above that. That way, they keep their transmit frequency clear with all the mess and put everybody up on that receive frequency so they can deal with it up there. So the answer is all of that good stuff. Kind of keeps everything in the clear and keeps their transmitting frequency clear as well. And it could be that some regions that would not be able to transmit on that particular frequency, some regions of the world. That's another reason for it. This is item A. Cabrillo format is the format that's used for submitting contest logs after we've had various contests. And the other format is ADIF. Also used for submitting log data, amateur data interchange format. During VHF, UHF, in which band segment would you expect to find the highest level of single-sided band or CW activity? The idea behind this is that you would call on a particular frequency and then go either side of that calling frequency to do your conversation. So in the weak signal segment of the band, you'd put the activity near the calling frequency, that is either above or below it, but it would be close to the calling frequency. You'd make your contact on the calling frequency, then move up or move down to carry on the conversation. Which of the following bands in amateur radio, or is amateur radio contesting generally excluded 30 meters, period? No contesting on 30. What's the function of the DX QSL card manager? Basically to handle getting the cards back and forth from various places to confirm the contacts that we've made with the other stations. The old paper QSL cards were nostalgic. Today we do a lot of that electronically, of course. Which of the following contacts could be confirmed using ARRL's logbook of the world? And you can use all of those. Matter of fact, you can use just about any kind of contact with logbook of the world. So all of those is correct. Okay, that's that particular section. Anybody have any questions, thoughts, or otherwise on that before we tackle the next one?
Yeah.
Okay, I'm going to share this spreadsheet with you just for a second. I had mentioned to a couple of you earlier that if after the session tonight, I could get you just to shoot me an email so I have your email address. I'd like to set up an email group with all of us so we can send things out to you. And one of the things I'd like to send to you is this little spreadsheet. This is kind of the idea of how I laid it out based on the numbers of questions and other things. And as you'll notice, down toward the bottom there, down toward session 7 and 8, there's some of those that don't have a whole lot of questions. That's kind of our makeup period. So if we get a little bit behind like we were from the last time, we have some time there where we can make up the distance, and I think we'll be just fine with it. But I thought you might like to see these things, and you kind of see where we're going. Over on the left, the chapter 1, 2, 3, 4 corresponds with Gordon West's materials in his book and in the slide deck that we're using, since we're using his slide deck. So with that, we're going to tackle outer space communications. And I guess I can just close that now, can I? Stop sharing, and give me just a moment to get my...
Bob, what's your email address?
Easy one is bob at rdcons.com. Romeo, Delta, Charlie, Oscar, November, Sierra, rdcons.com. Bob at rdcons.com. Okay, are we ready? Well, we'll share that one, and here we go on the next session. Let me share that one and put it in full mode, and away we go. All right. Which amateur stations are eligible to operate as Earth stations? Now, we're going to talk about a couple of terms here along the way. A space station would be something like a satellite station or something that's up in space. An Earth station is something that's on the ground, normally where we are. And we can communicate Earth to the satellite or from the satellite back to Earth. Generally, the satellite might send back telemetry data, or we might send command data to the satellite if we're in a position to do that. So that's kind of the orientation of where these questions initially are coming from. So which amateur stations are eligible to operate as an Earth station? And we might change that question just a little bit and say, who's authorized to operate an amateur radio station? Anybody who has the privileges to do that, right? Which gels with the answer to the question. Any amateur station subject to the privileges of the license class that the operator holds can be the Earth station. Doesn't matter whether we're talking to satellite or not. It's all the same definition. Okay, and we've explained that, I think, already. What is a space telecommand station? All right. An amateur station that transmits communications to initiate, modify, or terminate functions at the space station. If we're telecommand, meaning we're sending a command to the space station, whatever it happens to be, telling it to turn on or turn off or change frequency or decrease, increase power, shut down from one orbit or whatever it happens to be. So a space telecommand station is one which talks to those guys that are up in space to send them information to change or modify their behavior. What amateur stations are eligible to be telecommand stations of space stations, subject to the privileges of the class of operator license, which they hold, of course. So who can do that? If you got the license for it, you can do it. That's the bottom line. And any station that's so designated by the space station that gives you the permission to do that in concert with your license, and you're good to go. Any amateur station so designated by the space station licensee, the one holding the license for that. What is the definition of telemetry? Anybody want to tackle that before I click an answer? Going to be bashful. Okay, that's fine. Telemetry is when we're sending data in one direction. Most satellites do send back telemetry. Balloon launches, which we'll talk a little bit about in one of these sessions. Likewise, balloon launches. Balloons will often send back telemetry data to tell you how high they are and what direction and speed they're traveling and so forth, their elevation and everything else that goes with it. But it's a one-way transmission. It sends it down. It doesn't expect a return. Which of the following may transmit encrypted messages? This is a tricky one, or can be a little bit, because generally speaking, we always say we can't encrypt anything. That's part of the rule structure under which we operate. We can't encrypt our data. There is one exception, however. There is. if we're talking to the satellite, we might be sending control signals that we don't want anybody else to have the privilege of doing. In that case, we can encrypt those signals from the telecommand signals to or from the Space Telecommand Station. Those may be encrypted. That's as far as I know, that's the lone exception to the no encryption rule. What must be posted at the location of a station being operated by a telecommand owner within 50 kilometers of the Earth's surface? Well, talking about this from a practical standpoint, if I'm the telecommand station here at my house in Allen, Texas, I could have a copy of my station license. Wouldn't be a problem. I could put a label with my name, address, and telephone number on it out there with that station equipment. I could put a label with the name of the control operator. That could still be me or it could be somebody else. So that means that guess what? They're all correct. We do all of those. And those are things that the FCC could check if they wanted to. And I bring that up for a reason, because there's another question later on where we say the call sign is the only thing required because the FCC couldn't check these things on a satellite anyway if they wanted to. So that's why I mentioned that. Keplerian data, or KEPs as they're called. There are a bunch of parameters that define the orbit of the satellite. The ARRL sends these out. I'm not sure what the frequency is, if it's weekly or every other day or so. It's pretty regular anyway. It's just a list of all kinds of data. You can put that into a program, and that program then will determine for you where the satellite's going to be at any given time for whatever satellites are available at least. And if you're trying to contact a satellite, you'll know when it's going to break the horizon and where it's going to be on the horizon, how long it's going to take it to go from horizon to horizon, etc. Gives all those parameters for the orbit of the satellite. It gives a lot of information. If you're not doing satellite chasing, probably you look at that data, it won't mean much to you. It doesn't mean much to me when I just look at it. You really need a program in order to understand what that means. What is the direction of an ascending pass for an amateur satellite? The way I remember this, a satellite travels generally in an elliptical orbit. It's not a true circle. And as it goes around the Earth, when it's coming from toward the south and going toward the north, as we see north and south, we would say that it's going up. It's ascending from south to north. Conversely, if the satellite's going the other way, going from north to south, as far as we would reference it, then we would say it would be descending. So in this case, the direction of an ascending pass would be from south to the north, just thinking about the world itself and how the world looks as a globe, going from south to north. What type of satellite appears to stay in one position in the sky? It just parks itself there. That's a geostationary satellite. And there are those that do that and they don't move around, which is nice. You don't have to track them and figure out where they are. What is meant by the mode of an amateur radio satellite? We have to watch this one a little bit, because usually when we talk about modes, especially in HF, we're talking about AM or FM or FT8 or some other kind of C4 FM or something like that. But that's not what we mean here. The mode is actually the uplink and downlink frequency bands. There are letters assigned for the various frequencies, and those mode letters are the uplink, downlink frequency bands, indicate those. What do the letters indicate? Basically the same thing. Uplink, downlink frequency ranges. And those letters do specify a range. They'll say from this frequency to that frequency. So that's why we say frequency ranges for those letters, for the mode designators. And I pasted this chart in there so we could look at what that looks like. As you'll see, the HF frequency range is 21 to 30 megahertz, mode H. VHF 144, 146, mode V. UHF 435, 438, mode U. L band 1.26, 1.27, mode L. S band, mode S, down to K band, 24 gigahertz, as you can see that. So that's what the letters mean. Any questions on that? We're good. Okay. Based on that, what's the L band and the S band? And I just have to say it's the 23 and 13 centimeters. And that's the letters that were assigned. So if we go backward a little bit, you can see that L and S from there. Okay. Which of the following types of signals can be relayed through a linear transponder? Well, perhaps it's best first to say, what is a linear transponder? A linear transponder here we're talking about in a satellite. It's different from a repeater. Normally, a repeater will take a signal in, demodulate that signal, pull the information off of the radio signal, and then retransmit it on a different signal that's been remodulated with that same information. So it comes in one way, goes out at a different frequency. A transponder on the other side basically takes whatever comes in and just sends it right back out again on a different frequency sometimes, but not necessarily, usually on a different frequency. And it usually covers a whole band of frequencies, or a whole group of frequencies within a band for the transponder. So it may be actually transponding or sending back. Transferring might be a way to say it. Several different conversations, several different frequencies, all at one time. Okay, what kind of signals can be? Basically, the answer to that is anything you want, all of the above. You can put anything into a transponder, it'll come back out the same way on the other side. That's a linear transponder. There's another one we'll talk about here in just a moment. Okay, why should the effective radiated power of the ERP be limited to a satellite using a linear transponder? One of the characteristics of the linear transponder is to try to transmit back down the highest level power that it's detected. So if it detects a strong signal, it will tend to jack up the transmit power. So if we put a lot of power up to the satellite, it's going to try to duplicate that, which means it's going to run the battery down much quicker. And it won't be available for other users to use it if the batteries run down, quite obviously. So the rule then is to use the minimum ERP that you can get by with when you talk to a satellite that has a linear transponder that preserves its batteries so that everybody else can use it whenever they choose to do so. Questions on that? By the way, just stop me if you have a question. I won't be asking that all the time. Which of the following is characteristic of an inverting linear transponder? Now, we talked about just a transponder. An inverting transponder is a little bit different animal. It still does what the transponder does. However, it inverts the signals so that anything came in as upper sideband will come out as lower sideband, for example. So it does a lot of interesting stuff there as it's taking care of sending the signal back out again. It processes it quite differently, as you can see there. The Doppler shift is reduced. That's that changing of the frequency because uplink and downlink shifts are in opposite directions because everything's been flipped. Signal position in the band is reversed. As we said, the upper becomes lower, the lower becomes upper, upper sideband becomes lower, etc. How is an upload signal processed by an inverting linear transponder? Okay, it's going to go up. You're going to get mixed with a local oscillator signal, and the difference of that is going to be what's sent back down. That different signal has not been demodulated and remodulated. It's just taking that difference frequency, and that's what's going to be sent back down. The difference is what's going to cause the inversion by using the difference frequency. What type of an antenna can be used to minimize the effects of spin modulation and Faraday rotation? Most of the satellites tend to rotate a little bit, and their signal tends to do likewise. So if we can polarize our antenna in a circular polarization, it will tend to work a little better to offset some of the spin and some of the fade that goes on when we're tracking a satellite. So a circularly polarized antenna, for some reason, that's just difficult for me to say. Which of the following techniques is used by digital satellites to relay messages? The key here being relay. The satellite's going to pick it up, hold it until somebody else wants to pick it up. It's going to be relayed from me to somebody else. So that's called store and forward. Purpose of a digital store and forward functions on an amateur radio satellite. It's going to get it, hold it, and then send it out for somebody to download it just a little bit later on. Just going to hold on to it until that person receives it. Which of the following HF amateur bands include allocations for space stations? Not all bands are authorized on space stations, by the way, but all of our common bands are. The WARC bands are not. The WARC bands are not. So that leaves us with 40, 20, 15, and 10, the most popular ones that we use, and they each have an allocation for space stations. Which VHF amateur bands have frequencies authorized for space stations? And this is a little bit of a quirky kind of a question. There's actually only one there that works. That's the 2-meter one. And the way the wording is set on the rule, it just if you read the wording, it's a little quirky. If you just remember 2 meters is what's authorized for VHF and space stations. That's the key. Oh, wait, let me back up just a second. That had what I wanted to say there. Okay, the VHF band normally is 30 to 300 megahertz. However, we're only able to use the 2-meter band. We can't do the 1.25 meter, the 222 megahertz band, because the rule says it has to be 222 megahertz up. So that eliminates the 1.25 or 221 frequency band and puts us in the 2-meter range at 144 to 146. Okay. Which UHF amateur bands have frequencies authorized? Okay, and that's our standard UHF that we use, and then it's 13 centimeters in addition to that. What's the approximate maximum separation measured along the surface of the Earth between 2 stations communicating by EME? EME is excuse me, is Earth, Moon, Earth. I have to slow down when I say that, which means that I'm here on this Earth. I send the signal and bounce it off the moon. It comes back to the Earth where somebody else can receive it. Well, so what's the maximum separation between 2 stations, my station and somebody with whom I'm going to communicate by EME? So if I'm on this side of the world, basically that person's on the other side of the world, but they can see the moon. We got about 12,000 miles to work with. So if the moon is visible by both of us, that means we're eligible to do EME, Earth, Moon, Earth communications. What characterizes libration fading of the EME signal? Now there's a mouthful once again. And libration fading, I've got a slide that'll talk a little bit more about that in just a second. It's a fluttery, irregular fading. Excuse me just a moment. I've got somebody at my door. Pardon me just a sec. Hey guys, I can't right now. I'm in a conference. Can't do it right now. Okay, I'm sorry there. Okay, back to libration fading. It's a fluttery, irregular fading caused by the moon's wobble in its orbit just a little bit, plus all of the little irregularities on the moon's surface. That's essentially what that boils down to. And I picked up a definition there. You can read that definition if that helps any. Of course, the answer to the question is the fluttery sound with rapid, irregular fading, called libration fading, caused by the wobble of the moon and some of its roughness on its surface. Everybody okay with that? Everybody need more time to read that?
I didn't know the moon vibrated.
Yep, kind of shakes as it goes, if you please. Okay. When scheduling an EME contact, which of these conditions would result in the least path loss? And we get into some crazy terms. Anybody know what apogee and perigee is? If you ever dealt with rocket launches and that sort of thing, you kind of get into there. Perigee is the key word here. When the moon is closest to the Earth is what that boils down to. Apogee, on the other hand, is when it's the farthest away from the Earth. And I think I put a little note there about that. Apogee is the pointed orbit. That's when it's farthest from the Earth. Perigee is closest to the Earth.
So the worst time is if it's right overhead, right?
When it's closest to the Earth. Yeah, when the distance, the less the distance, the better. Exactly. Mm-hmm. if the moon is going way away from you, then if it's a long ways further off than normal in its orbit, then that makes it more difficult. Yeah, exactly. Okay. And did we say that? No, we didn't. Method for establishing contacts. You need to have some kind of a schedule with somebody else and figure out exactly what time we're going to do what. That is, we synchronize our stations so that that station knows that we're going to do this at a given time as the moon comes up. Okay. Which of the following digital modes is designed for that? Any thoughts? This was a special one. It's not MSK44. That was something else, you remember. Q65, and that is correct. Has anybody ever used Q65?
I have, just trying it out.
Have you? Okay.
Yeah.
I've never used that. I'd be interested to see it work, see what it sounds like. It'd be interesting to see.
Call me anytime. We'll give it a go, Bob.
All right. Maybe make a moon contact with somebody. That would be interesting to see that. I'll keep that one in mind. Okay. Thanks, David.
We can just do regular feature. We don't have to use the moon.
Okay. Well, I guess that's true too. Sure. Okay. Q65. What's the characteristic of the JT65 mode? Anybody want to jump on that one? What's special about the JT signals and all that? What's their main characteristic? They pull a signal out that you can't even hear with your ear. So that's the case with this one too. Pull that signal out, even though the signal to noise ratio might not be so good. What type of modulation does it use? And I don't remember. Multitone audio frequency shift keying, AFSK. We'll probably talk a little bit more about audio frequency shift keying a little bit later on. Basically, it's saying we're using several tones and we're switching back and forth between those tones. Let's see if there's anything there. I don't think so. I think we're okay with that. Let's go on. What does the 4 in FT4 mean? Anybody have a thought about that? We'll cheat. 4-tone, 4 for 4 tones. 4-tone continuous phase frequency shift keying. So makes some interesting sounds, to say the least. Most of the WSJT modes use a multi-tone baseband signal, which FT4, FT8 are both a pair of those, of course. What technology is used for real-time tracking of balloons? There's where we get into balloons. How do we track a balloon as it goes away from us? What service do we use for that? A lot of us have that particular service on a lot of our radios if we just want to call it up. APRS. Exactly, APRS. Now, automatic packet reporting system. Let's see, what was there? There used to be another term, another definition of the term, but I don't remember what it was now. Anyway,
automatic
APRS. Position reporting. That was it. That was the one other one that it was called oftentimes. Yes. I don't know if any of you track the balloons that the Richardson Club and Plano Club sometimes go together and launch, but they have that information reported to a particular website, and it actually will show you where the balloon is and how high it is. And sometimes they have a good camera on there taking pictures. You can actually look at the pictures and all that. So APRS works wonderfully well, even for a balloon. Which of the following is required in the identification transmissions from a balloon-borne telemetry station? Just the call sign. That's all. That's about all you really need to do is just give the call sign. Now, a lot of the people will program those things so they get more than that. They'll get more telemetry than that. They'll get the altitude and the speed and the rise, the ascent rate as it rises and so forth. But the call sign is the only thing that's required to be sent, which makes sense, of course. Okay, we're at the end of that one. Any thoughts about that? Questions? Comments? We got a few more minutes. We'll tackle a little bit more. All right, let's see. We did that one. Back up. Now we're into session 2, and we want to do that one. All right. With that, let me back into here, and we're going to share again. That screen, share it, and tell it to Give us a slideshow. Visuals and video. This is where it takes me back to the old days of TV service, the stuff I'd forgotten along the way. But it's just kind of interesting stuff. Okay, slow scan TV. We have slow scan TV and fast scan TV we can use in amateur radio. Slow scan TV is used on the HF ranges. The fast scan TV normally is only used on the UHF frequencies, and there's some good reasons for that. So how is color information sent? And these signals are analog again. We're not sending them digital per se. How are we sending the color information for it? Well, we're going to send them one at a time, basically. One line at a time. That's why it's slow. We're sending them one line at a time. Okay, and we just had somebody else come in. Come in, Terry. Okay. Okay, what aspect of an analog slow scan television signal encodes the brightness? Brightness or the luminance is the traditional TV term for that. However, it has to do with the tone's frequency. As the frequency goes up, the brightness increases. And what signals in single side or slow scan TV receiving software begin a new picture line? There are some specific tone frequencies that key that and say this is the beginning of a new line. So the data from here for so many milliseconds down and so far down will give you a line of picture information. And that tone is there to remind the software, hey, it's time for a new line. The function of the vertical interval signaling code, or VIS code, is sent as part of an SSTV transmission to identify the mode. There is a signal first that comes in that tells the software what kind of mode, because there's several modes we can actually use for slow scan TV. So we get a quick signal there that indicates during the vertical interval what mode that this particular transmitter is using. So we're looking at the mode to identify the mode. And to think about that one for a second. What kind of a receiver can be used to receive and decode slow scan TV signals using the digital radio mondial transform? And I'm not sure I'm pronouncing that right. DRM protocol. DRM for me means digital rights management. I have to watch that one anyway. But at any rate, kind of receiver, basically your regular SSB single sideband receivers are used to do that. The digital radio mondial is really more fluff in that question than anything seriously having anything to do with it. Which of the following is an acceptable bandwidth for digital voice or slow scan TV transmissions made on the HF amateur bands? Okay, generally speaking, what are the limits for voice? We go from 0 to what frequencies is considered voice range? 0 to 3 kilohertz. That's correct. And that's the same here. 3 kilohertz is still the same for voice. What technique allows commercial analog TV receivers to be used for fast scan TV operators in the 70 centimeter band? 70 centimeter, obviously being the 430 area, 430 megahertz area. And this is where we can use, if you have a TV that will receive cable TV channels, it can actually receive some of those things if you're able to tune it in and actually get it tuned in. It will suppose, I've never tried it, but it's supposed to work. I have to take that one on face value. The key there being it's capable of doing cable TV on the TV set. In digital television, what's the coding rate of 3/4 mean? Okay, it means there's 4 bits of information. The first 3 are actually information, and the 4th has some forward error correction data built into it so that it can correct something if something comes through wrong. So it's 3 and 4. All righty. 4 bits total, 3 of it actually contains data. The 4th contains error correction information. As they mentioned here, it's not great, but it works. So, hey, let's don't argue with success. And this gets us back into the old TV world. How many horizontal lines make up a fast scan television frame? This takes us back to the old days of analog TV sets. We had 525 horizontal lines, and we're still using that today. The NTSC standard National Television Standards Committee set the 525 horizontal lines on the regular TV in the old days. We would actually do 262 and a half lines in one pass. In this next pass, we would do the next 262 and a half lines interlaced with the first group. So, of course, it's doing it so fast that your eye didn't catch the movement, but it would give you a much more clear, much sharper picture by doing it. But the total number of lines is 525 lines for fast scan, like the old TV days. How is an interlaced scanning pattern generated in fast scan? Well, that's what we were just talking about there, by the way. We'll scan one line, come back and scan the other line. And we do that with the odd and even numbered lines. We'll do one odd number line, and come back next time, do the even number in between the previous lines. What type of modulation is used for amateur television DVB? Digital video something terrestrial signals? And that's one I don't know, but you just have to know. QAM and QPSK. Q standing for quadrature. QAM and QPSK. That's one I think you just kind of have to add to your memory banks. Digital video broadcasting terrestrial. That's what that term stood for. QAM, QPSK. Vestigial sidebands. We get into this and hadn't dealt with that in a long time either. What is vestigial sideband modification? It's where we take one whole sideband and send that out, and we just take a part of a second sideband that gets transmitted. We don't do full double band transmission, so I think that's going to be A. Yep. Again, I'm kind of going right on through. If you have a question or you want to kick it around or otherwise, please stop me on that. We do have a 6 megahertz bandwidth for a standard analog TV signal, so we got to keep everything within that 6 megahertz channel. Which of the following describes the use of vestigial sideband and analog fast scan? See, vestigial sideband reduces the bandwidth while increasing the fidelity of low-frequency video components, and that's just a factor in the way it's mathematically laid out. And that's not a very long one, so that works out pretty quick. We may even get pretty close to being back on schedule, you know. Let's see if we can get the next one. Now, this next one is quite a bit longer, so I doubt that we'll get this one finished. But we'll get into it. We'll do what we can. Everybody okay?
Yeah.
Good, sir. Yep. Sir.
All righty, let's make it happen. Yeah. Okay, here we go. Which of the following types of modulation is used for data emissions below 30 megahertz in our HF range, if you please? Which type of modulation? Frequency shift keying. That's data, meaning digital, by the way. Everything is FSK something. Audio FSK, various other things that we might use for that. What's the difference between direct FSK and audio AFS, and AFSK, which is audio FSK? And with FSK, the frequency shift keying is going to actually modulate the transmitter to give us the output frequency that we want, whereas the audio AFSK modulates the audio frequencies themselves rather than the output of the transmitter itself. So direct modulates the transmitter's variable frequency oscillator. A common cause of overmodulation for audio frequency shift keying, this probably is one of the more obvious ones, excessive audio levels. If we turn the audio gain way up, it causes overmodulation and garbage. Of course, that's also true with just irregular FM video voice communications. If we have the mic gain turned up way too high, we overmodulate and it sounds terrible. And that's true here as well. Excessive audio causes overmodulation. What parameter evaluates distortion of an audio frequency shift keying signal caused by excessive input audio levels. What's it going to mess with? It's going to mess with one of those things we don't normally get into that much called intermodulation distortion, or IMD. That's one of the things that you often will look at in specifications when you look at specifications for transmitters and receivers. But anyway, if we put excessive audio in there, we mess with the IMD, the intermodulation distortion, as it's called. What is considered an acceptable maximum intermodulation distortion level for an idling PSK signal. In other words, it's idling, meaning it's not sending data right then. And minus 30 dB is considered, that's the maximum noise that it can be putting out. Minus 30 dB is one of those answers. And it mentions here, the bigger the negative number, the better it is. So if you're looking at the specifications for a receiver or a transmitter, if the IMD products are greater than minus 30, like minus 40, then that's a lot better. Why should the phase of a PSK signal be changed at the zero crossing of the RF signal? That's got a whole bunch of terms mixed in together with all this thing. PSK. Somebody help me. What does the P stand for in PSK? I just went blank.
Phase.
Pardon?
Phase.
Phase shift keying. That's that. Yes, of course. Thank you. The brain wasn't there for that one, I suppose. Okay. When we're doing PSK, the software that comes with it, oftentimes, that we use with it anyway, oftentimes has a little indicator up in one corner of the screen. And what we're looking for is this zero crossing point in that little indicator. It will show two elliptical circles. And one of those two elliptical circles, one vertical, one horizontal, superimpose over each other and center up in that window across each other so they're not distorted in either direction. They're pretty much equidistant all the way around. Then that's called the zero crossing point of the signal. And that's when the PSK signal will be the best. And the best signal, the least splatter, anything else, and doesn't give you a lot of splatter around the band. It's nice and clean and crisp, and it's easy for the receiver to decode it as well. There's a little tuning thing you can do in the software for that takes care of that. Okay, Q65 and JT65. Any ideas? Okay. In Q65, we average some of the cycles. This is particularly used, I understand, in the very low frequency ranges of our amateur bands. Average it out to get an average of the signal, which gives us a better signal, of course. And this is one I think everybody will know. How long is an FT8 transmission cycle?
15.
15 seconds. You got it. That was the standard. All righty. What's the relationship between symbol rate and the baud? Okay, they're basically the same. They're just two different terms for almost the same thing. For all intents and purposes, as it says here, they are the same. And it mentions here the number of symbols per character may determine the ultimate data rate, but not the bandwidth itself. As far as the bandwidth is concerned, they're the same. What's the definition of symbol rate in a digital transmission? And this is kind of an unusual answer there, the rate which the waveform changes to convey the information. So basically the waveform is changing as the digital signals change. And the symbol rate is indicated. How many symbols can we send based on how many times that waveform changes, i.e. a new symbol is being transmitted. Key, waveform changes. Which of the digital modes has the highest data throughput under clear communications conditions? Anybody have a thought on that one? Highest data throughput. Okay. PACTOR is something most of us won't have too much to deal with. PACTOR requires some special equipment in order to make it work. In my mind, it's kind of expensive, but it does work. It's been around for a long, long time. We had PACTOR in different iterations. There's PACTOR 2, PACTOR 3, and PACTOR 4 is the current one. But as I said, it does take a special piece of equipment in order to deal with PACTOR. does send data through it pretty fast. Which of the following modes can be used to transfer data, binary files, i.e. send a file from my station to your station? We can actually do that with PSK31, believe it. Oh, I'm sorry. You can do some things like that, but not what they're looking for. PACTOR, because PACTOR can send a lot of data quite fast and very accurately. So that's why they're saying PACTOR. I'm sorry, I overstepped the bounds on that one. My apologies. PACTOR, binary file transfers. Okay. And it uses the acknowledge and the negative acknowledge, i.e., it sends out information, and then the receiving sends back an acknowledge if everything's okay, or a negative acknowledge if it wasn't, which is a request to resend that particular block of data that was just sent. So they can pretty well go back and forth as long as the atmosphere is clean, and then they can go pretty fast. If the noise comes up and it gets pretty dirty, then that's a whole other ball game. It slows down. Okay, we'll take this, and this will be our last question for tonight, since 8 o'clock is right on us right now. What are some of the differences between Baudot and ASCII? Okay, Baudot is an old code that's been around for the days of teletype, way back when. ASCII stands for American Standard Code for Information Interchange. Two different codes. They both transmit information, but they're a little bit different. The Baudot code uses 5 bits. ASCII code has 8 bits, but it normally only uses 7 of those. So what's the good answer here? Let's see. Baudot uses 7 data bits per character. Nope, it doesn't. Baudot uses 5 data bits per character. ASCII uses 7 or 8 on answer B. Baudot uses 2 characters as letters, figures, shift codes. ASCII has none. Yep. Okay, I'll accept B. Another point on this: the Baudot does not, in one pass, have upper and lowercase letters. You have to send it a shift code and shift it from lower to upper or vice versa in order to get the second character set. The ASCII code, on the other hand, since it has more bits to work with, has upper and lower at the same time without having to shift back and forth. So B is actually the answer they're looking for here. Baudot is 5 bits per character. ASCII is 7 or 8. Actually, allocates 8. The 8th one may or may not be used. The Baudot uses 2 characters as for shifting codes. ASCII does not do that. It just sends it. Okay, with that, I'm going to stop that, and I'm going to stop that. Okay, gang. Any thoughts, comments, questions, heartburn, headaches, etc.? You're going to be easy on the old guy tonight, huh?
Yeah, you did good. Thank you.
Very good, Bob. Thanks. Thank you, Bob.
Okay. I'm going to do a quick capture on the attendance. We got that. Okay. In case some of you may have missed it, which you may have if you came in a little bit later on, I had asked that if everybody would just send me an email, bob@rdcons.com, rdcons.com, that I'll have your email address. I'm going to put that into an email group so that I can send you some things. I'll send you the schedule that I showed you in the beginning in the spreadsheet, and so you kind of have an idea where we're going. Part of that is so if you're studying and you're not using the Gordon West material, you can kind of have an idea of what the topics are. Gordon tends to put things together by topic, whereas the ARRL takes them in the same order that they're listed in the question database, which sometimes don't have a whole lot of relationship to previous questions. Gordon tends to make them put in a lineup. By the way, I did receive the ARRL book. That's the beast. You see how thick that sucker's an inch thick? 8.5 by 11. It's huge, but it's a great book. It has a lot of good information in it, a lot of good discussions of the questions. If you have questions about why does this work or how is this laid out, it's a good place to get information. So for whatever that's worth. Okay. Anything else from anybody before we shut her down for the night?
No, sir.
Thank you, gang. I appreciate you being here, and we'll do it again next week, same time, same station, as they say, and we'll pick it up where we left off tonight. Okay.
All right.
Thanks,
Thank
Bob.
you.
Okay.
Okay.
Good night,
Thanks,
everybody. Have a great week. Great weekend.